We've talked about the effects of groups that are attached to the benzene ring on where the electrophile comes in. We've talked about the resonance effects, but we have not yet talked about the inductive effect. And so we said that these groups here that are electron donating groups by resonance are going to pump electron density into the ring, making it a better nucleophile and making it react faster at the ortho and para positions. And then these groups that are electron withdrawing by resonance are going to pull electron density away from the ring, especially in the ortho and para positions, and make it a worse nucleophile and in those positions, leaving only the meta position for it to react in. So let's think about what the effect, the inductive effect is of these same four groups that I have listed down below there. Remember what the inductive effect is? If you have a bond and the electrons or the atoms that are attached to the bond are not equal electronegativity, excuse me, the electrons are going to be closer to the more electronegative atom. And so the inductive effect of the carbon-chlorine bond is that the chlorine is pulling the electron density towards it away from the ring. And so by the inductive effect, the chlorine is electron withdrawing, even though by resonance it's donating. So nitrogen is not nearly as electronegative as chlorine, but it's more electronegative than carbon, and by the inductive effect, the nitrogen is electron withdrawing. The amino group is an electron withdrawing group by the inductive effect. When we have an aldehyde here, the oxygen is pulling electrons density away from the carbon towards it, and then you know how the inductive effect works, right? It's very strong when it's on the next atom, and then as it gets further away, it gets weaker and weaker. Well, this is not an electronegative atom attached to the ring like these are. It's two atoms away, but still there's an inductive effect. It's pulling electron density away from the first carbon, which pulls it away from the second carbon a little bit, and so we still have the electron withdrawing inductive effect. So these groups that have a pi bond between the first atom and the second atom have the same electron withdrawing inductive effect. All of these groups that either have the first atom being electronegative or the second atom being electronegative are going to have an inductive effect, and they're all going to be electron withdrawing. So if we fill in this table here, we have the electron withdrawing inductive effect of the chlorine, of the amino group, of the aldehyde, and of the nitrile. So with these groups that were electron withdrawing by resonance, they're also electron withdrawing by induction, and so both of these are going to deactivate the ring, or deactivate, I can't talk and write at the same time. They're going to deactivate the ring by making it a worse nucleophile by pulling electron density away by resonance and pulling it away by the inductive effect. In the first two examples, we're going to have a competing effect. And the first example, we have the chlorine, which is electron donating by resonance. And remember, resonance is going to put a positive charge on chlorine, and so it's not, chlorine's electronegative, it doesn't really want to have that positive charge, so it's not going to be as strong an effect as maybe an amino group. So amino group, if it's electron donating to a benzene ring, will end up having a positive charge on the nitrogen. Nitrogen's more electropositive than chlorine, and nitrogen can handle it better. So the actual the electron donating effect by resonance is greater for this group than it is for this group. So this nitrogen's more electropositive, so it can handle the positive charge when it's donating its electron pair by resonance. At any rate, we have a competition between induction and resonance in both of these groups. And with halogens, the inductive effect, which is very strong, pulling electron density towards this electronegative atom, wins out. And so in the end, it's donating electron density by resonance, pulling it away by induction, and in the end it pulls away more than it donates, and so it is also deactivating. So that's going to deactivate the ring, and that's going to deactivate the ring only weakly. These groups down here are going to be strong deactivators because they are pulling away electron density by both the resonance and the inductive effect. And then for the amino group, it turns out the donating effect is much greater than the withdrawing effect by the induction, and so that wins out significantly. And so this is going to make the ring a better activator, or better nucleophile. It's going to activate, and it's going to be a strong activator. And there's a table in your book, and I'll see if I can shove the book underneath my ring stand and apparatus here. It might be a little bit shaky, but we can try anyway. I'm going to lift this up and move it over. And can I move it up so you can see that? Yeah, okay. On the top of page 495, we have this nice summary of all of these different types of groups. And they are going from, and the figure here is classifying these groups as orthopara-directors or meta-directors, and you can see that down below. And then they're classified on a scale going from the strongest deactivators to the strongest activators here. So all of these are electron withdrawing groups by induction and by resonance, and they are going to deactivate the ring, making it a weaker nucleophile and making whatever electrophile come in go to the meta position. These halogens here are orthopara-directors because they have a lone pair there, but the inductive effect is stronger, barely stronger than the resonance effect, and so the inductive effect is withdrawing, and so the net effect is that these are going to be weak deactivators. They're going to make the ring a little bit worse nucleophile than it was without a halogen on it. And then we will ignore these for the time being and then jump to the ones that you're familiar with here with the lone pairs that are next to on the first atom, and these are going to be all strong activators. We know that they're deactivating by the inductive effect, but they're activating by resonance, and the resonance wins out, so these are strong activators. So this is the grouping here, and this is going to be important for knowing whether something is an orthopara-director or a meta-director, and whether they're activators or deactivators, because, well, just a little jump ahead, we have been talking about having one group on the ring and adding a second one. What if we have two groups on the ring and they have competing effects? What is going to win out? And so we're going to end up getting, again, things that we're interested in, as pharmaceutical compounds may have three groups on the ring, and we may have to synthesize those. So if we put two groups on the ring and they're competing against each other, directing the third one to a specific position, which will win out. And this will help us to sort that all out. The other thing that I wanted to show you is on the previous page. So if you've got your textbook out, then keep it open, because on the next video we're going to look at the table that's at the bottom of the previous page. And that's an interesting table because it shows you relative percentages of ortho, meta, and para products, so you can see how important this difference is. When we say that the major product is meta, how major is it? When we say the major products are ortho and para, is it going to be more ortho, more para? Well, it depends on the group, and we will talk about that in the next video.